I want to talk about some common things that we might do with the graph, traverse it. And I want to talk about the standard traversals. This question is titled, what are the standard traversals and how are they related? Let's take a look. Here I'm going to model this graph, this tree, where the ultimate node, the ultimate ancestor node, the root is A and the leaves are D, E, and F, and we have B and C here. There are many different ways for me to transition, to visit every node in this graph. I can visit every node by visiting them in level order, visiting everything at this level, then everything at this level, then everything at this level. I can visit the nodes via some sort of depth first search, find everything that's connected to A first, and then when you hit a dead end, a leaf, back up, and then go down to E, and then back up, and then go back up to A, and then go to C and F. And in fact, there are names for these traversals. Here is the same modeling. This is a NetworkX-esque modeling without using NetworkX. And here is the canonical implementation of that first traversal, what we call a pre-order traversal. A pre-order traversal is a traversal where you visit a node the moment you register a node the moment you visit it. A post-order traversal is when you register a node after you visited all of its children. An in-order traversal is when you register a node in between registering the left-hand child and the right-hand child. And this code won't quite work because I haven't enforced that this is a binary tree. And a level order traversal is what happens when you visit or when you register a node after you visited all of its children. If we run these traversals, we'll see exactly what we expect for the pre-order, the post-order, the in-order. Now, typically, it's the case that people don't really talk that much about the post-order and the in-order. Largely, these can be converted from and to each other. It's really the pre-order and the level order that we talk about the most because this corresponds to our notion of a depth-first search. Go to all the children before you backtrack, and this corresponds to our notion of a breadth-first search. Visit everything you can before proceeding. And when you think about that, you might say, well, you know what? If this is my approval process that I'm trying to model, if it gets blocked up, what do I do first? Do I try and get all the approvals all the way down to the most senior level? Or do I get all the approvals at my level first and then go to the next level and then go to the next level? And based off of your business use case, you may want to look at a traversal of this form. Level order traversals come up quite a bit, not in the form of the level order traversal when we talk about things like BFS and DFS. But one thing that I want to draw your attention to is for my level order traversal, I implemented this without recursion. I implemented this with a deck. And it turns out that I can actually implement all of these traversals without any kind of recursion. This is the pre-order traversal implemented without recursion using a very simple formulation for converting any recursive formulation of a function into an equivalent iterative formulation by just taking the implicit stack that the recursive formulation does and make it implicit in the data. And one of the interesting things we can see about the breadth-first search and the depth-first search, about the pre-order and the level order traversal is they're the same algorithm. The only difference is the data structure. A pre-order traversal is just a traversal using a stack, pushing and popping in, first out order. And a level order traversal is the same thing using here not a stack, but a queue, registering nodes and dealing with nodes in a first in, last out approach. And because the algorithms are largely identical, I can actually implement them themselves. Here you can see they work the way that I expect them to work as long as I fix one small thing here. It's really the same algorithm, just one using a stack and one using a queue. In fact, I can write them as the same algorithm, and I can say all the pre-order is just swap out the operations, the initialization, pop and push, and checking if empty operation on the data structure. And the level order is basically the same thing with just a very, very tiny conceit just to get the ordering of these nodes right, just to match up to the left and right-handedness of the graph as I have demonstrated. But you can see these traversals are basically the same idea. It's just a different data structure. Now let's convert this over to our NetworkX frame of view. And with the NetworkX digraph that looks something like this, with A connected to B and C, B connected to D and E, and C connected to F and G, we can express the same idea in terms of BFS edges, DFS edges, and the topological sort. The BFS edges gives all of the edges of this graph in that breadth first order, the DFS edges in that depth first order, and the topological sort, which is very, very interesting. You can see it matches just to the level ordering. Topological sort is one of the top things that I do on with traversals on a graph, because if that graph represents some kind of dependencies, the topological sorting gives me all the dependencies that I have to meet before I can move on. So if, for example, this code here represents packages that I need to install, and it's the case that A is dependent on, or A is a dependency for B and C, and B is a dependency for D and E, and F and G's dependency is C. So for example, this might be libc, this might be libreadline, this might be libmath, and this might be my Python interpreter and a Python package, or maybe this is my Python interpreter and these are two packages, and this might be my Ruby interpreter and two packages. I can use the topological sort to identify the order in which to install these. You install the rootmost, and then you can install these two next levels. And what I could do is I could even figure out how to parallelize these if I were to amend this topological sort with the depth. If it's not just the node, but also the depth, then I can install the items in parallel if they're at the same depth. And so when you think about workflows like make-based workflows or workflows that are implicit from, for example, software dependencies, this topological sort shows up immediately because it shows you what you can do in parallel, what's not blocked. And so this gives you a little bit of a sense of the standard traversals: breadth first search, depth first search, in order, post order, pre-order traversals, level order traversals, and a little bit of a sense of what you can do with these when you apply these to the graphs that might come up in your work.